please send the link to.
Hello, hello, hello. Hello all. Hello all, thanks for joining in. If you can see my screen and if my voice is clearly visible, can you please drop text in the chat box, please, in the live chat. Hi all, so we are starting. Please do call your friends if some of them want this live. I want the chat box to be active enough, so please do react whenever I ask for something so I can see if you understood well or not. Alright, so let's proceed, guys. Yeah, so talking about digital design, you don't have microprocess, anyways. So talking about digital design, right? So you talk about systems, you talk about various systems which does some function, right? Which takes in some input and does something, right? So taking a core structure of digital design in essence, firstly we learn about the number systems, right? How basic number systems work in computers. Secondly, we learn about Boolean algebra and simple reduction techniques, and then simple combinational circuit design techniques, and we'll be looking through various interesting circuits and their logic behind it. And then sequential circuit, we might have a break in between 1, 2 and 3, and then lastly we have programmable logic devices, and then followed by you have Verilog, right? So getting started with unit 1 now. So if you're all fine with it, can we move on? Can you all react? Please do drop a text. Yeah, sure. Okay, guys. So talking about number systems. So what are the different base systems we have? Firstly, decimal and binary, octal and hexadecimal. Decimal of base 10, 2, 8 and 16, right? So we'll learn about conversions between one system to another, and then we learn about one's complement, two's complement systems, and that should be the basic of this chapter, right? So digital systems operate on discrete elements of data, which are just discrete things, and here whatever we are going to deal with in the basic level of computers is just zeros and ones, right? Now we represent them in terms of different levels. In binary it is zeros and ones. In decimal systems it is going to be 10 numbers, which is 0 to 9. So 10 digits are going to be there, that's why deci, right? Similarly, for so this is an interesting one. So why do we use binary things? Because it's flexible enough to represent that in a computer system, right? So you can implement them using circuits very easily. You need a capacitor and a transistor, right? And simple levels of high and low, right? So that is also there, and this is how basic organization of a computer looks like, right? You will put instructions in it, input, and that's going to be processed, and you can store it whenever you want it, you can process it whenever you want it. There are always going to be control signals here and there, correct? Now you can have a state present and you cannot have a state present. So basically you can rely on the past inputs and you may not rely on the past inputs, and just input output processing is a combinational circuit, but something which keeps recurring based on some external logic, based on a clock or something, you call it what? A sequential circuit, and that we'll discuss towards the end of this chapter, right? and a digital counter does some function. So these are all several circuits which are interested in this particular course. And so let's move on to the part which is most focused here. So yeah, decimal numbers. So normally how do you represent numbers? 5, 6, 3, 4, just 5 into 10 so we have place values, right? So for every number system you talk about will have a place value. So this will be 10 power 0, 10 power 1, 10 power 2, 10 power 3, 5 into 10 power 3 plus 6 into 10 power 2 plus 3 into 10 power 1 plus 4 into 10 power 0. So you call this all these tens as what? Radix, right? So for a decimal system it's 10. For a binary system it's 2, for an hexadecimal system it's 16, and for an octal system it's 8, right? And you know the digits and all. So for radix R, what are the digits available? 0 to R minus 1, right? So let's quickly, so hope you all know this, right? So you can do that for all these set of numbers. So this is for decimal numbers, this is for octal, 4 into 8 power 3, plus 5 into 8 power 2, plus 3 into 8 power 1, plus 6 into 8 power 0. The same thing. And if you have fractions, just put 8 power minus 1 and minus 2, right? So this will be minus 1, this will be minus 2, and so on. And you can do that for binary numbers as well. Group of 8 bits is going to be byte, and group of 4 bits is called a nibble, right? And you know why you use binary, because it's simple enough, and that is implementable, right? So you can implement, you can tolerate your noise, and you can transmit data over time by just simply building binary circuits. Bi meaning 2. So how do you convert between one system to another system? You have a decimal number, you want to convert it to a binary system. So how do you make it? Firstly, the decimal number would be in something like, let's say 65, right? So you'll progressively divide it by 2, we'll see, right? And record all the reminders and read the remainder in the reverse order, right? So just recapping that, what if you have a binary number, you want to take it to decimal, you will see what are the place values of that binary, and you'll take all those place values multiplied by the number at that place value, and you will add all of them, right? So something like 101. What is the place value at this position? This is just 2 power 0. This is 2 power 1. This is 2 power 2, right? So the place value is just going to be 1. I'll add it to this. This is just 0 plus the place value here is 4. So total it's a number 5. So simple one, right? And then how do you convert any binary number to any octal number, any binary number to any hexadecimal number? Again, so you have a binary number, you will group it into threes. You'll group it into threes to realize an octal number, right? From the right to the left. Similarly, if you have a binary number, you will group it into fours from the right to left, right? To realize an hexadecimal number. Let's say I write a random number, okay? Something like this, okay? This is a random number. Now, I want to make this an octal number. I'll just put this as 3, 3, and then 3, right? Now, I'll realize each of these 3 bits as what? One particular octal number, right? I know 110 is what? 6, and 101, 5. 010 is going to be 2, right? So this is one full octal number, right? So you can do that for hexadecimal as well. You will just group them into 4 instead of 3. Instead of 3, you will just group them into 4, right? Similarly, right? So you will group them into 4, and you know this hexadecimal, right? So it will be 0 to 9, and then A to F, right? F being 15. So you know all that. And whenever you want to convert a decimal number to hexadecimal, a decimal number to octal, you always have a bridge which is binary, which will help you in doing that. Again, that is feasible enough, right? I mean, there's also a method. You can always divide it by 8, record all the reminders, and put them in the reverse order, just like how you do it for binary. But that is not required as of now. Or you can just simply convert it to binary, and you can split them into 3 or 4 bits and realize that number in the respective conversion systems. With this, till this point, is everything clear for all of you? Can you please react something so I can confirm? Okay, sure. Now, moving forward, let's try to see how to convert with these decimal bits, right? So how do you convert that? If you have this 0.6 or something, what are you going to do? Convert 46 to binary, and you will record all the reminders and write them in the reverse order. Now, whenever you have this numbers after the decimal point, you are going to successively multiply it by 2. Okay, so you'll take this as 0.6875 and you will multiply it by 2. you will get what? Something in 1.2 something, 1.3 something, right? And then you will record that 1 and put it there. That will form the first binary number, right? 1. And then you will take that, you will realize the 0.8 by 2, you'll get 0.7500. You get 0, you put it there, and then you take the remaining ones, 0.7500, you'll multiply it by 2, you get 1.5 something. You'll take what? 1 there, and then you get 0.5000, you multiply it by 2, you get 1.000. You'll take the 1 and put the remaining. You multiply it by 2, you always get 0, so 0, 0, 0, 0. There are chances you might get this keep repeating, okay? You can stop it till a certain number of bits, right? So that's also always feasible. So I've told you all this, right? And then given the number of bits, okay, you will always see that m will always be less than or equal to 2 power n minus 1. M will always be less than or equal to 2 power n minus 1. What do we mean by this system? Let's say you want to represent this. So how many bits are required to represent decimal bits, decimal digits with a binary code? So decimal, so you're wanting to put what? 10 things, right? M is going to be what? 10. But the number of bits available is what? The number of bits which can be put in a binary code would be nothing but just 2 power n minus 1. So 2 power n minus 1 would always be greater than m. Since m is going to be 10, 2 power something should always be greater than, because I want to put this greater. If I put 1 here, it will be 2 power 0, which is not greater. If I put 2 here, no. If I put 3 here, no, because 2 power 3 would be just 2 power 3 minus 1, which would be nothing but what? 2 power 2. So if I put 4 here, n minus 4, it will be what? 2 power 3, right? 2 power 3. I mean, this should be 2 power n minus 1, could be lesser, but 2 power n from m should be greater than or equal to m, and then greater than 2 power n minus 1. So one sec, sorry for the confusion, I'm just repeating that point again. You will have 2 power n greater than or equal to m greater than 2 power n minus 1. Right? So 2 power 4 is very much feasible to accommodate 10 bits because 16, right? So that's the whole point here. So just understand this one, and that should do. Yeah, so all these systems, right? So whenever you have a decimal number like this, 0, 1 till so 0 to 9 are the digits, and then you'll have all the numbers successively. Whenever you want to represent that in BCD, just put all the numbers in 4-bit representations. You know the respective numbers binary, right? So just put them in 4 bits. So 0 is just 0, 0, 0, 0, and 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. I advise you to look at all these things once at least, so that you will understand this. So, and then following XS3 is just plus 3 of binary. Whatever you had for binary, just do plus 3. So 0 plus 3 is 3. So what is 3 in binary? 6 plus 3 is 9. So what is 9 in binary? Just put that, right? And you know how to represent in binary, and you know how to represent in octal. So octal will be 0 to 7, and successively from 8, you will just start from 1, 0, 1, 0, right? So you don't have a digit called 8 in octal, right? The digits are only limited to 7, 0 to 7. So from 8, you will just keep 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, and then for hexadecimal, it is from A, B, C, D, and so on, right? And gray codes. So gray codes, these are very much important in error detection, right? So in error detection, and in K-maps also you use this, right? So what is the remarkable feature of the gray codes? It is nothing but the 1-bit change. So what do I mean by 1-bit change? You look at these. Firstly, we'll see how this is going to be converted, and then we'll move forward with how these systems work, how you can implement this, right? So 0, 0, 0, 0 is there, 0, 0, 0, 1 is there. You see how many bits are getting changed to make this number, 0 to 1, just 1 bit. How many bits are changed to make this number, just 1 bit, just 1 bit, right? So you see the difference, right? So whenever you have 1-bit change, you use what? Gray codes. Again, error detection, and you use this in K-maps as well for the same sake of it, right? Now, how do we deduce this? So whenever you have a binary number, you want to convert that binary number to gray number. Okay, gray. So let's call the binary number as some 4 bits, random 4 bits, B0, B1, B2, B3. So to convert this to gray code, what you'll do is, you will copy that exact MSB position as it is. So B3 will just become G3. Okay. And then you will compare B3 and B2. You will see if B3 and B2 are going to be same. If they are going to be same, you will put what? You will put 0. Right? right? Else you will put what? 1, right? So you'll compare B3 and B2. If it's going to be same, put 0, different, put 1. Similarly, you'll compare B2 and B1, same, different, you'll put the respective bit, and you'll stop it, right? So that is the binary to gray conversion. We'll see through an example. So you have 1 0 0 1 1 0. So copy this 1 and then compare different, so put 1. 0 0 compare same 0. 0 1 compare different 1, and so on, right? How do you convert a gray code to binary? So it's the same procedure. See here. So this is a gray code number which you have, right? So put the same MSB portion here, right? Now you'll compare this bit not with, so what did we do in the binary to gray conversion? We compare this bit and this bit, right? If they are going to be same, we put 0 there. But that is not the case here. So you will compare the bit which you got with the bit which you have next, right? So 1 and 1 same, so 0. 0 and 0 same, 0. 0 and 1 different, 1, and so on. So you obtain the same binary number, right? So this is the binary to gray conversion and gray to binary conversion. I hope this should be clear, right? So yeah. So these are all, so you are not weighting any, there are no weights. So we applied place values there. So there are no weights here. And this is going to be called a reflected binary code. Yeah. And in modern digital communications, gray codes is used in error communications, error corrections, and K-maps also uses what? Gray codes, right? And we saw BCDs. So how do you add numbers? Very simple. You will have a number like this, right? What do? You take, so this, hereafter we'll be only dealing with binary numbers, right? So what happens here? You have a bit, another bit, you will add them. 1 plus 1 will be what? 2. 2 in binary is 1 0, so you'll put 0 here and carry 1 here. 0 and 1 is 1, 1 plus 1 is 0, so 2, so you'll put 0 here and carry 1 here, and so on. You'll keep doing this. Simple addition, right? Simple addition. And how do you do subtraction? Subtraction can be done in the normal way also, but mostly subtraction is preferred to be done in 2's complement way, in which you represent negative numbers. We'll be seeing that number systems in a while, but understand subtractions can be done normally here. So what happens? 1 minus 1 is 0. 0 minus 1, you cannot subtract 0 from 1, so you'll borrow 1 here, right? So it will become 2. So 2 minus 1 is 1, and then you have borrowed here 0, so 0 and 1 again, so you'll borrow 1 over there, so it will be 2 minus 1 1, and you'll get 0 here. 0 minus 0 is 0, and you can do the rest of it as it is, right? And binary multiplication, whenever you have, so you want to multiply a binary number by binary number, you will have these sort of bits. So you'll multiply the 0 by all of these bits, right? So 0 into 1 is 0, 0, so 0 into anything will be 0 only. You'll copy all of it. Similarly, if you have 1, you will copy the entire thing, 1 0 1 1 1, 1 0 1 1 1. You will just leave a value here. Similarly, if you have zeros, all zeros. If you have ones, just copy the whole number. Now it's just addition, right? So simple multiplication. And then error detection. So very simple. You will use error detection to minimize this things which happens during this networking, right? So whenever you are transferring data from one medium to another medium, the chances that it will get mixed up. The data could be modified. So to identify whether the data has been modified or not, you associate various methodologies. One of the methodologies could be what? A simple, parity bit, right? So redundancy is just some extra information which you put to realize whether an error is there or not. Now parity. Talking about parity, very simple. You will have a binary number. Okay. So there are two kinds of parity: even parity and odd parity. So you will put an extra bit to this number based on the type of parity. If it's going to be even parity, right, you will make sure that the total number of ones in that word is even. If it's going to be odd parity, you'll make sure the total number of ones in that number is odd. So basically, you will be given a binary number. You will see the last digit in that binary number, and you'll see all the digits in the binary number. You will add a parity bit in such a way that if it's going to be an odd parity, so a system will be just one of these, right? It will be either odd, or even, right? So if it's going to be odd, let's say, what do? You will see a number of ones in that. If the number of ones in that is even, then you have to, if it's going to be an odd parity system, you will add one more one there, right? So very simple one. So let's see here. We have 100,011. So this is the number which we want to represent. Okay. So what do? You will see this number. How many ones are there? It's going to be 2, 3, right? So if the number of ones is going to be odd and it's an even parity system, you add one more one. Simple one. If it's going to be an odd parity one, you put 0 so that the total number of ones will be what? Odd. So you can always do this, right? So whenever you have a set of numbers and you want to maintain even or odd parity, what do? You will try to what? If this is going to be even parity, you'll just put what? 0, because if you put 1 there, the total number of ones become odd, which is not the even parity system. So that is the case. Very simple one. And ASCII characters are used to represent these. So because we saw how to represent numbers, but how to represent words, how to represent letters. So you have ASCII values. For the corresponding ASCII values, you have the corresponding hexadecimal and binary values, which you can reference, which you can use for representing them in the basic level of computers, right? Following that, we have the sign number systems, positive and negative numbers. You have the sign bit. The sign bit will tell you whether it is positive or negative. This 0 represents that. So basically we have these 3 number systems, right? Sign, magnitude, 1's complement, 2's complement systems. Sign magnitude being the simplest system. You want to represent 12 in sign magnitude system. You will first write the binary representation of 12, which is nothing but 1100. Let's say it is going to be 8-bit, so let's make that standard 000. So you'll put the MSB position to be 0, then you call it plus 12. If you put the MSB position as 1, you call it minus 12. So as simple as that, right? So that's going to be the sign magnitude representation. And the range of sign magnitude values is going to be what? It will range from minus 2 power n minus 1 minus 1 to 2 power n minus 1 minus 1. What do I mean by this? So if you take n as the number of bits, let's say the number of bits is what? Just 3 bits. I'm only having 3 bits. So what can I do? I can represent 2 power 3 minus 1. So 2 power 2 minus 1. So minus 2 power 2 minus 1 to 2 power 2 minus 1. Meaning I can represent what? I can represent from minus, so 4 minus 1. So minus 3 to plus 3. Simpler one, minus 3 to plus 3. And there is a glitch here. So what is a glitch? So when we put n is equal to 3, we put 2 power 3 minus 1. So 2 power 3 was what? N is 3. So 2 power 2 minus 1. So 4 minus 1, 3, right? So minus 3 to plus 3 we had it. But there was a glitch here. So what was a glitch? Because it's going to be a sign magnitude, according to the steps which I carry out, for 0, I can easily put 0, 0, 0, right? I can also put 1, 0, 0. Right? This will be regarded as plus 0, this will be regarded as minus 0, but technically there are no minus 0, there is no plus 0, there is no minus 0, right? It's neither negative or positive, right? So what do? You will have to formulate a system which will take care of this issue. So this issue exists in sign magnitude system. So just remember that. Now following 1's complement systems, are you all with me now? Yeah? Okay. Following with 1's complement system, you will invert all your bits, right? So in 1's complement system, you will be given a binary number. Whenever there is going to be a 0, the 1's complement of that is going to be 1, right? So 0, 0, 1, 1, 0, 0, 1, 1. So what happens? You will put all the zeros as 1s and all the 1s as zeros. So it will be 1, 1, 0, 0, 1, 1, 0, 0, as simple as that, right? So you can directly convert that using this formula as well. And you can just do this, right? So put all the zeros as 1s and 1s as zeros. That will give you the 1's complement of it. And what do you mean by 2's complement? Just do 1's complement plus 1. Firstly, before that, we'll just do these range also. So what is the range for this? So in sign magnitude, what was the range? We talked about minus 2 power n minus 1 to 2 power n minus 1 minus 1. It's the same range here. So it just the bracket is taken outside. Anyways. So again, this also has the same issue of plus 0 and minus 0. You know that, right? Plus 0 is 0, 0, 0, 0, which is the same binary representation. If you invert this, 1, 1, 1, 1. Again, minus 0. I don't want this, right? So that is there in this 1's complement system, right? So that issue was also there. Now, in 2's complement system, what happens? To resolve that issue, you are adding 1 to it. So 2's complement system is nothing but just 1's complement system plus 1. Right, 1's complement system plus 1. So this was the expression which we got for 1's complement, right? Plus 1, right? So whenever you have something, right? Whenever you have something like this, right? 0, 0, 1, 1, 0, 0, 1, 1. What is 1's complement for it? 1, 1, 0, 0, 1, 1, 0, 0. Just add 1 more to it. So how do you add it? Just the last bit will be 1. That's it, right? So very simple, very straightforward. Let's try to deduce this. So this table is very much important for you to understand these number systems. Please go through this. So in normal decimal systems, how do you make it? you will always have 0 till 1 to 7, minus 1 to minus 8. So whatever, you will have successive numbers from, you will have all these integers, right? All these decimal numbers. Now, whenever you are putting it in sign magnitude, whenever there is going to be what? So let's try to deduce the logic here. We know that whenever you have a number of bits to be what? Let's say in this case it's going to be number of bits, 4. Then the range of values which are available for sign magnitude is nothing but what? Minus 2 power 4 minus 1 to plus 2 power 4 minus 1, which is nothing but what? Minus 2 power 4 minus 1, sorry. Yeah, what is that? That's going to be what? Minus 2 power 3 minus 1. So minus 2 power 3 to plus 7. You see here, minus 7 to plus 7. Similarly, the same range, minus 7 to plus 7. You don't have any extra numbers there, right? But takes one number extra from that range. You remember, right? So if you see at this, minus 2 power n minus 1, there is no minus 1 here. You see that? There is only minus 2 power n minus 1. 2 power n minus 1 minus 1. So in the negative region, a number is extra. In the positive region, it's the same. So understand, in all these systems which we discussed till now, in the positive region, all the numbers are going to be the same, right? 0, all zeros, right? 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, which are simple binary numbers, right? If it's going to be the negative numbers, in that case only the numbers will differ. If it's going to be minus 1, what do? You take the binary number, put 1 in the MSB position, right? So that's going to be the simple one. All the numbers you had here, instead of 0 here, which represent positive, put 1 on all these places, right? In ones complement system, just invert all the bits, right? So simple, just invert all. I mean, you don't invert the bits for a positive number, only for a negative number, right? So in minus 2 in ones complement system is what? You write it in the normal binary number, which is nothing but what? 0010, right? Now, what do you do? Whenever you have 0010 and you want to write what? In 2's complement system, just invert all the bits 1101. Simple as simple as that. You can do that in one's complement system. And 2's complement system, just add 1 to this, add 1 to this, add 1 to this, add 1 to this. Now we had an issue there, right? We had two representations for 0, plus 0 and minus 0, right? So how do we tackle that? So plus 0 was 0, 0, 0, 0. Okay. In one's complement, if you do, it will be 1, 1, 1, 1. But you are adding plus 1 to this, right? So if you add plus 1, it will become what? It will become 0, 0, 0, 0. There will be 1 0 here, but you will ignore that. Because your system will only take the bits up to which it is allocated for, right? If it is allocated only 4 bits, it will only take those 4 bits. So technically 0, 0, 0 is the same number for both of these cases, plus 0 and minus 0, right? This issue is resolved in the 2's complement system. So just doing that. So how do you add numbers? How do you subtract numbers? Add numbers, we just saw it, right? You just add the numbers using simple one's complement. Just represent numbers in the one's complement form, just add them. So 0 plus 1, just 1. 0 plus 0, 0. 1 plus 0, 1, and so on, right? Very simple one. How do you add something in 2's complement system? It's the same thing. I mean, both of the systems does not differ in the way they are added. Okay, just subtract it. I'll show you. I mean, even in that case, I'll show you what's the difference. So what happens here? Whenever you're adding numbers here, you get a carry here, and you add that carry in the last position, right? So you're adding everything in a certain number system. You get a carry here, you put that in the last, and you add it to the final result. Right? Now you want to do this. 12 minus 1, subtraction, using one's complement system. Now whenever you want to do subtraction, understand that subtraction is just a sister of addition. Okay, so 12 minus 1, so 12 plus of minus 1, right? First write 12 in binary, which is 1100. What is 1 in binary? 1 in binary is just 0001. But I want to represent this in one's complement system. So you will put that in what? Invert all the bits. 1 1 1 0. So 1 1 1 0. I'll just add all of them. So for convenience, I'm putting, because all these numbers are 4-bit things, I'll always add more bits to it so that we represent it properly in a standard system, right? So that's why I put one more 0 here. I put 1 here. Right, I put one more 0 here, right? So what happens here? Just add them, and you will get your answer, right? Whatever n carry you are getting, you will finally add it. To the same procedure, right? Same thing in 2's complement system. What do? You just ignore it. So I'll show you how it is done. So you add it here. So 1100 000, just add it random. It does not make any significant difference here. So what happens when you put 2's complement? Because you're adding 1, already when you're doing the 2's complement of the number itself, 1's complement plus 1, right? You'll ignore whatever carry comes here because your system realizes only till that standard, right? So let's try to do this same problem. 12 minus 1. So what happens? 12 in binary is just 1 1 0 0, and minus 1 is nothing but what? Plus 1 is 0 0 0 1. Okay, and in 1's complement is 1 1 1 0. 1's complement plus 1, so 1 1 1 1, right? 1 1 1 1. So that's going to be the 2's complement representation. So what do you do? Again, I told you, you will just add that with the 2's complement number system. So this is what? This is plus 12, and this is what? This is minus 1 in 2's complement system. In 2's complement system, right? Now you just add this. Just add this. So what happens? 1 1 0 1. So 1 1. So you get what? 1 0. What do? You will just ignore the last bit because you already added it. That's it, right? So that is ignored, right? Similarly, you can do what? You can do 13 minus 5 also. 13 is what? 0 1 1 0 1, and 5 is, it's because this is positive, we are not inverting this and stuff, right? In 2's complement system, positive numbers are the same. Now if you take what? 5, because this is going to be minus 5, you take plus 5. What is plus 5? The plus 5 is just 1 0 1. In this case 5 bits, let's take 0 0 1 0 1. Invert all the bits, 1 1 0 1 1 0, right? So 1 1 0 1 0. Now add 1 to it, so this will become just 1, right? Now add both of them, and whenever you get a carry, right? Whenever you get a carry, you'll just ignore it, okay? And when you're doing this sign multiplication, right? So discarding the carry bit, the sign bit is seen to be 0, indicating a correct result. So basically, you will always take this. So basically, you know that 13 minus 5 is what? 8, and you know that plus 8, it's going to be plus 8. So if it's going to be a plus, you'll always observe, even in the table, whenever you saw the positive numbers and negative numbers always had a 0 in the MSB, and negative numbers always had a 1 in the MSB, right? So you'll always see that. And here you ignore this carry and you see the MSB portion easily. You easily see it. The sign bit is 0, and your logical operation which you did was correct. Now, moving forward with this, give me a second. Yeah, so that should be clear, right? So that should be the essential of it. Now, simple digital circuits, you know that digital circuits operate on digital data. There is a very interesting concept in analog to digital conversion. I'm just telling a basic of it. Just knowing digital design, you should know this. So whenever you have an analog signal, right, like this, you'll always break them into parts. You'll break them into parts in definite intervals, rigid intervals, right? You will see what value it corresponds to. A responsive value it corresponds to. You will break them into patterns, okay? And you will group them into various groups of classes. You will round it off basically. You will round it off, and you will make them high, low, and you will get a progressive high-low signal for respective signals, for respective points in your analog signal, right? So ADC, which is analog to digital converter, does this, right? So it will convert everything to steps, just putting things into approximations, right? So that is what it is. So we saw all of this. Digital circuits are accurate than analog. We know that. Digital circuits are relevant because capturing analog data is first tedious, okay, and capturing analog data and processing and all is very much difficult. So that's why digital circuits work. Yeah, and you have all these gates, AND gates. So simple logic of the gates. So AND gate, you'll get many inputs and you will get one output. But whatever inputs you're getting, you will see if even one of the inputs is going to be 0. If even one of them is 0, the output will be 0. Else the output will be 1. Or to put it in other words, only if all the bits are going to be true, it will return 1. Else it will return 0. All the bits are going to be 1, it will return 1. Similarly, or even one of them is 1, it will return 1. Simpler one. This is a simple NOT gate. It will invert the bit. NAND is just a NOT. You will perform AND and then you will perform NOT. Right? And then NOR, you will perform OR and then you will perform NOT. XOR, we did something for gray codes, right? We compared this bit and the next subsequent adjacent bit, and we saw whether they are same or different. If they were same, we put 0. If they are different, we put 1. Actually, what we were using in that case was a simple XOR gate. A simple XOR gate. We were comparing both. 0 and 0 are same, we put 0. 0 or 1 are different, you put 1. 1 and 0 are different, 1. 1, 1, 0. So very simple one, right? XOR is just not of XOR, right? So just understand that, and that should be the end of unit 1. If you have any queries, you can drop it in the comment section. Is it all clear, all of you? Can you please drop a text? We will get back to you. Just give us 2 to 3 minutes. அதுவும் இல்லை கண்டிப்பாக கிடையாது.
இன்னும் அவுட்புட் கேப்சர் தான் வரும் நான்.
அவன் என்னமோ சொன்னான் எனக்கு தெரிஞ்சு.
யாரு?
கமலேஷ். Do we really want to record this?
Yes, of course.
Please.
பண்ணாண்டா.
I don't want to record this.
சப்பாரா இருந்தாலும் there should be something for them to get back to. உனக்கு நல்லா எடுக்கணும்னு நினச்சினா you can take it tomorrow also. அவங்களுக்கு ஆஃப்லைன் எடுக்கலாம் நீ. பட் ஒரு இப்போ நம்ம உட்காந்துட்டோம்னா யூடியூப்ல there should be something.
சரி ஓகே புரியுது.
ஆட் பண்ணிடுறா கேப்சரு. அவுட்புட் கேப்சர் போட்டியா? இப்போ இன்புட் கேப்சர் தூக்கிடு. டபுள்
ஆட் சோர்ஸா? நோ remove Hello guys. So starting with unit 2, right? So Boolean algebra. So what do we understand from the term Boolean? Boolean refers to a variable in programming, right? So Boolean just talks about two things: 0 or 1, true or false, high or low, on or off, whatever, right? So this only talks about two states, right? So in binary systems and computers, we always work with two things. So there are always variables which accounts for either one of these values, right? And based on these variables, you can form expressions, you can form circuits which will do multi-level, processing for you, right? So in this case, Boolean algebra is just a system which will do this manipulation of variables, right? These are created by various operations. We earlier saw we have different gates, right? So AND gate, if both are going to be 1, then only it will return 1. All other cases it will give you 0. In OR, even if one of them is 1, it will give you 1, otherwise 0. NOT will just reverse the bit, right? And whenever we talk about a Boolean function, obviously a function will take an input. It will always take input from the set 0 or 1, right? And there will always be a Boolean operator which can be AND, OR, and so on. And there will always be one Boolean variable, right? So Boolean variable will attain what value? Either true or false, correct? And output will always be what? True or false again. Very simple. So how do you formulate a truth table for this? Very simple to understand. First, see how many inputs are going to be there. There are going to be 3 inputs. Then what are the possible combinations of inputs which you can form? 2 power 3, because each input can be 0 or 1, 0 or 1, 0 or 1. So you can form literally 2 power 3 inputs. Now put all of them and try z bar plus y. You will take the whatever z table corresponds to and invert all the bits of z. If it's 0, 1, 1, 0, 0, 1 and so on, right? Now you will take z bar and similarly you will take x. So you will compare the value of x and z bar. 0, 1, you are ANDing it. So even if 1, 0 is there, it will be 0, right? So xz bar will be 0. Similarly, even 1, 0, 0, 1, 0, 0, 1, 0, 0. 1 and 1, you compare 1. 1 and 0, 0, and so on, right? And you'll compare xz bar and y, right? Because xz bar and y are going to be OR, right? So even if 1, 1 is there, it will be 1, right? So 0, 0, there is no 1. 0, 0, there is no 1. 1, 0, there is a 1. So you will just compare each and every bit and you will just do this. So xz bar plus y. Now simple theorems, very simple, straightforward, right? So x plus 0 will be x, and whenever you have 1 in an OR expression, it will always be 1, and in 0 in an AND expression, it will always be 0, right? And yeah, and these are called like x plus x will always be x, x dot x is x. Just to remember, x plus xy will be x, because if you take x common, it will be 1 plus y. 1 plus y will always be 1, so x dot 1 will be x, right? Similarly, x into x plus y will be x, because x dot x plus x dot y. X dot x is nothing but x, so x plus y, which is again x only, right? So the same thing applies. X plus x bar will be 1. So why do we learn this? We learn this for Boolean simplification. So towards the end of the chapter, we might be assessed for simple Boolean simplification. So those things are there, right? So we also have this xy plus xy bar. You can take x common, then what happens? Y plus y bar becomes 1. And x plus y into x plus y bar, you can just multiply sequentially x into x dot x. One sec, please. Give me a second. Yeah. So we might have x plus xy plus xy bar. So we took common there, right? Similarly, we multiplied x and x, so x dot x. Similarly, x and y bar, xy bar. We multiply this x dot x plus xy bar plus yx plus yy bar. What is yy bar? Something and its complement, you are ANDing it. There will always be a 0 in there. So this will be what? 0, right? So it will be just x plus xy bar plus xy. Technically, what is that? X plus x, which is x, right? So simpler one. You can always do that for all the other theorems. I want you to note this last one, right? What is this? Xy bar plus y. Or you can write it in other words also. X plus x bar y will always be what? X plus y. X plus x bar y. So some variable plus that variable's complement into some other variable will give you what? That same variable plus the other variable, right? So very simple to understand. There is a law called distributive law. Distributivity over or, right? That is applied here because you are distributing and or not, and or over and, right? So what happens here? You will distribute this in this way. So x plus x bar y is nothing but x plus x bar dot x plus y. right? X plus x bar will always be 1. So 1 dot x plus y, you'll just get x plus y. Simpler to understand, I guess. So moving forward, and you can always do this, right? So to attain from here, you want to attain till this position, you can always multiply whatever variables are not there by just doing dot 1. By doing dot 1, you can replace that 1 by whatever variables you want it to be, and you can simplify it further to get this expression, right? So simpler. Operator precedence, you will first do the parenthesis 1 and then you will do the not 1, which follows De Morgan's law. What is that? A plus b or x plus y, the whole bar is nothing but x bar, y bar, but plus will be changed to dot. Similarly, x dot y, the whole bar would be nothing but x bar, y bar, but dot will be changed to plus. That's it, right? So not and or, we all have that. So this is inversion. You can always do this, right? You can always find the complements of each of them. How do you do that? You will take the overall not. How do you take the overall not? You will see these two expressions. So this is one expression, this is one expression, which is ANDed. So you will put it as what? A bar plus b whole bar, and c bar was already there. You will bar it, you will get c, and this dot will be replaced by plus, right? Now you can do the same thing inside and you can get the expression, right? So I'll do that for you. So this bar is there is a plus here, so you'll replace it by a dot and take that bar, and you'll also complement the individual ones, so it'll just become AB bar, right? So simpler one, right? So that's the you can always do that for other things, right? So there are multiple laws, you can just take a look at them, right? And dual is simple. What happens? You will replace every AND by an OR. You replace every OR by an AND, right? Plus by dot and dot by plus. 1 by 0 and 0 by 1. Simpler one. So you see here minus x dot 1. What happens? Minus x will be there. Dot will become plus. 1 will become 0. Plus will become dot. And minus y will be minus y. Plus will become dot. And this will be just z, right? And you'll just put brackets for convenience, alright? So yeah, so this is how it will be. Now min terms and max terms. So this is where things get interesting. So you will have few variables, and all these variables can take up different terms. So let's say you have just two variables a and b. You can express them in different ways. Either you can complement all of them, you can complement none of them, or one of them. So ab is one combination, a bar b is another, a b bar is another, a bar b bar is another, right? You have names to each of them. Whenever you call it a min term is the minimum guy, right? So you will name this guy small m, right? Small m followed by a subscript. How do you find the subscript of it? See, understand this. In min terms, the actual variable is termed to be what? 1. And the complemented variable is termed to be what? 0. Right? So whenever you are talking about the corresponding min term for a term, a bar, b bar, let's say, a bar is nothing but what? A bar complemented, so 0. B bar complemented, 0. So technically 0, 0 in binary is what? 0. So technically m naught is represented by a bar, b bar, right? Similarly, this is going to be 1, 0, right? So that will be what? M2. Similarly, this will be what? 0, 1, M1. This will be 1, 1, this will be M3. And so on. You can always do that for 3 bits also. So given a number of variables, you can generate 2 power n min terms, right? So that is also there. So see this, easy to understand, just in 3 things. So a, b bar, c bar, 1, 0, 0, m4, small m4. Now talking about max terms, you do the same thing,